Let us talk about the geometric progression. When we discussed the arithmetic progression, what we found was that with the arithmetic progression, you start with a number, the first term, you add a number to it to get the second term. Then whatever you added to the first to get the second, you added that same number to the second to get the third term. That same number you added to the second to get the third. In order to get the fourth, you add it to the third. So you keep adding that number to get the next term. Well, with geometric progression, what you do, well, the argument is the same except that you now multiply instead of add. Now, the geometric progression is generated when we start with a number, say A. We use A to represent that number, and we repeatedly multiply by a fixed non-zero constant. So you multiply by a constant R. We use R to represent that constant, and it must not be zero. All right? So that's what it's saying here. Now, as for the terms of the geometric progression, let's take a look at them. You start with the number A. We use A as a variable. You want to get the next number. And remember, by the way, we're talking about geometric sequence. It's just that it's called geometric progression. Progression is a popular name for it. When you multiply A by the constant R, you get A times R. Good. Now, you want the third term, so you multiply this now by the constant. Again, so you have AR and you multiply by R. But what does that give you? It's AR squared. So we can just write AR squared. Next, to get the next term, you multiply this by AR. By R, I mean. So you have AR squared times R. But what is R squared times R? It is R cubed. So I could just write this as R cubed instead. So it's AR cubed. Then to get the next term, this is the fourth term. To get the fifth term, you take the third term, AR cubed, and multiply by R. Now when you multiply R cubed by R, you get R to the fourth. So I can just call this R to the power of 4. And so on and so forth. So remember, this is the first term. The positions of the term. This is position 1, the first term. This is the second term that's in position 2. In position 3, you have the third term. In position 4, the fourth position, you have the fourth term. And you have the fifth term. And so on and so forth. Alright? Now, notice what happened here. The power of R is 1 less than the position that the term is in. So, let's say for the third term, you have AR to the. Now, if you write the position of the term here, then you minus 1 from it, you get AR to the 2. AR to the 3 minus 1 is AR squared. For the fourth term, what you have is AR to the 3, to the power of 3. But this can be written AR to the 4 minus 1. If you want to show the power in the expression, I show 4, but I have to minus 1 to get the 3. In position number 5, I have AR to the fourth, but instead of having AR to the fourth, I want to show the 5 to show the fifth position. So I erase the fourth and call it 5 minus 1. For the second term, this would be AR to the 2 minus 1, because AR means the same as AR to the 1. Now what about A? Well, A, if I want to show the R here as well, I would have to have R to the 0. Now R to the 0 is 1. So that's why I didn't really need to write it down. I just show A. But I want to show the R now. And I want to show the position that this term is in. So in position number 1, you have AR to the, I want to show the 1, but I must minus 1 now. 1 minus 1 is 0, so it's AR to the 0, which is the same as R. R to the 0 is the same as 1. Alright? So, you can say that the number A is the first term and R is a common ratio. So R is called the common ratio of the sequence. Then the nth term is a geometric sequence given by AN is AR to the n minus 1. Let me write that down. So what you have here is the nth term. Now the nth term, you call it A subscript n. It is equal to AR to the n minus 1. Alright? So here the nth term is AR to the n minus 1. The fifth term is AR to the 5 minus 1. The fourth term is AR to the 4 minus 1. The third term is AR to the 3 minus 1. The second term is AR to the 2 minus 1. The first term is AR to the 1 minus 1. So AN, the nth term, is AR to the n minus 1. So there you have the terms of the geometric sequence or the geometric progression. So remember now, you start with a certain number, we call it A, right? And you get the next number by multiplying A by a constant. Our constant is what we call R, which is a common ratio. Now, as to why they call it a common ratio. If you want to know what R is, when you're given the terms of a geometric sequence, what you do, just take any term and divide by the term before it. Why? Because when you found a certain term, you multiply the term before it by R. So you need to go in the opposite direction to get R. You divide by the term before it. So here, you take the fifth term, which is AR to the fourth, divide it by the fourth term, which is AR to the 3. A cancels A. R to the fourth over R to the 3 is what? It's going to be R. Because remember, R to the fourth is R times R times R times R. You have 4 R's multiplied together, divided by R to the 3, which is R times R times R. Now, these R's will cancel each other, and you have 1 R left over. Same thing you would get if you take the fourth term, divide by the third term. If you divide the fourth term by the third term, you get R. If you divide the third term by the second term, you get R. If you divide the second term by the first term, you get R. Any term divided by the term before it, you get R, the common ratio. And this is why they call it a ratio. Remember, ratio between two numbers, if you divide them, what you have there is the ratio. Alright? So A is the first term, R is the common ratio. Common because it's common to all of them. Alright? So there you have it. We're going to talk more about the geometric progression in other videos. So I will see you in the next video.